Hello, everybody. I'm going to do this Zoom for you for our chapter 1, and this will be the pattern for the way I do Zooms for the rest of the lectures for our class. You'll notice I changed backgrounds here and there throughout our class, so you're not always seeing the same thing, but you are seeing me. I might not always have a sunburned nose either. We had our outdoor activities this past weekend for the campus, distance always, of course, but I was out in the sun for 4 hours, and thus it looks like I have the sort of proverbial red nose. I could be Kurt the red-nosed reindeer, or maybe it just means I've had too many beers or something like that. As I'm recording this, it's in the morning, so chances are good it's not the beer. But I'm going to go through a bit for our chapter 1, so you can follow along as you would like to. I will share my screen, and let's see if I can actually make our share the screen thing happen. There we go, yay. So I'm up in the corner, and so we will get onto our slideshow. Play from the start. This is our first chapter, and we want to know what it is we're going to be doing in this class. We're going to be talking about astronomy. Astronomy means different kinds of things, and just note it's not astrology, it's astronomy. If you're still calling it astrology at the end of the semester, I promise you I will fail you, because astrology is not it. We'll talk about the difference later. I've even had people come up to me in the hallway like a year later and say, ah ha ha, I like your astrology class. And I said, ah ha ha, I can still change your grade with the registrar. So yeah, astronomy is not astrology. Astronomy is the study of the universe. We look at the sun and planets, and in fact, that's what we'll really be looking at here in this class. We can also look at things outside of our solar system, stars, which cluster into galaxies. Galaxies are collections of stars. Then the galaxies themselves group together into clusters. We live in the local group, which has a couple of dozen galaxies, and it's part of a larger supercluster with thousands of galaxies. We can look at life in the universe. That's often called astrobiology. And we can look at all sorts of things like time and time travel and warping space and gravity and the beginning and the end of the universe. That's often called cosmology. It's really only been in the last 100 years or so that we have been able to see really far and really deep into the universe. In fact, this year, 1920 to 2020, is the 100th anniversary of what was called the Great Debate. And the Great Debate was, are these things that you're seeing here all inside of our galaxy, or are there things outside of our galaxy? We didn't know there was anything more than just our galaxy. The universe was actually pretty small by comparison to today. We now know that there are hundreds of billions of galaxies that are out there, all of which have billions to hundreds of billions, sometimes to trillions of stars. So it is actually quite a diverse place out in the universe. Lots of different kinds of things out there. Up in the upper corner, you can see a star formation process taking place. That's a nebula. Nebula is a word from the Latin that means cloud, and this is where stars are being born. Down below, the lower picture, you can see a galaxy that is far from our galaxy. It's outside of our galaxy, and it has, as you can see, some dark material. That is not dark matter. That's a different kind of thing, but this is gas and dust that will eventually form into stars and other planets. But as we look out into the universe, we're also looking back into time, because things take time to get to us. Light travel is not instantaneous. So when we look out into the solar system, we're usually looking only a few minutes into the past. When we're looking at other galaxies, we're looking millions or even billions of years ago. Here we can see two different galaxies. This is an image from the Hubble Space Telescope. And you can see two different galaxies. Here's one, and here's another. And gravity is pulling them together. The reason why it's interesting to look at things like this is our galaxy is right now screaming towards another galaxy, or it's screaming towards us. We're actually pulling each other in, the Andromeda galaxy, and eventually we will merge. We will collide like these two are here. It'll take a couple of billion years though, so don't plan to go out and take pictures of it anytime soon. We do have some up close and personal kinds of photos with all of our planets in our solar system because we've had probes go to all of them. So what we can see here is a close-up image of Mars, and we will look at each of the planets in detail as we go through our semester. This is another nebula, but this nebula in particular is the remnant of a stellar explosion. This is called the Crab Nebula. And when this star exploded, you could see it in the daytime and you could read by it at night. It was very, very bright. It exploded for us, we saw it in the year 1054, so just about 1,000 years ago. One of the interesting things you note here in this picture, look how it's bluish in the middle and reddish on the edges here. With a little bit of green thrown in. That's Roy G. Biv. You may remember our friend Roy G. Biv from earlier science classes in high school and middle school. Those are the colors of the rainbow: red, orange, yellow, blue, green, blue, indigo, and violet. Well, that's actually how our sky works also. If you think about the sky, I'm looking outside right now, it's mid-morning, the sky is blue. But if I'd gotten up to watch the sunrise, it would have looked closer to this, reddish and orange. If I wait until sunset, looking out the window again, it will look reddish and orange again. This is the sky inside out. This is sunrise, this is midday, this is sunset. So we can see some interesting things the way light works out there. This is a picture you saw before. This is where stars are being born inside the gas and dust that is coalescing in the Orion Nebula. If you go out, especially in the winter time, to look for the Orion constellation, it's got 3 main stars. If you hold your hand up to the leftmost star and go about halfway down, you can just hold your hand out like that and go about halfway down, that's where the Orion Nebula is. And if you have really good binoculars or even a sort of somewhat good telescope, you can actually make it out as long as you don't have too much light pollution there. But this is a stellar nursery. Stars are being born here. We live on planet Earth. Welcome home. We are part of a solar system with planets and other things around the sun. The sun is one star in the Milky Way galaxy. We've got anywhere from 100 to 400 billion stars. This star is on the edge of the galaxy, notice. We're sort of in the rural background of our galaxy. That's good for us because in the middle, there's a lot of interesting stuff. And interesting in astronomy often means radiation. So yeah, it's good for us to be in the countryside as we speak. We are part of the local group. We are one galaxy among several dozen. There are 2 large galaxies. We're one of the large ones. Andromeda is the other, and I mentioned we're sort of pulling on each other. And our group is part of the local supercluster that is part of the larger universe. So that's where we are. We know a lot of this stuff because we've been looking at the sky for thousands of years. We've been looking at it through telescopes for hundreds of years. About 1610, 1611 is the operative date for telescopes. And we've been putting telescopes above the atmosphere so we can get rid of the atmospheric interference for about the last 40 to 50 years. The Hubble itself has been up in orbit for about 30 years. And this is a picture of the Hubble. It was only rated to last about 10 to 12 years, so we've really done well for it to be still operating 30 years later. But of course, we are here on planet Earth. We are a planet. We can see different features just from looking at this picture. We have this blue stuff, that's called water. We have this white stuff, that's also called water. We call clouds and water vapor and other kinds of things, but that's also H2O. Then we've got near the poles some other white stuff. That's also water. That's H2O, ice and snow. We've got this green stuff. That's life growing. It's largely the result of the fact that we have water on the surface. We also have an atmosphere. So we have land, we have water, we have all sorts of things that are made up in our planetary system. And we will look at that specifically in a chapter where we look at Earth as a planet. You've probably never seen this picture before because when you often see pictures of the Earth and the Moon, they're side by side. But in fact, the moon is quite far away. So if you're looking at it to scale, that means you're taking the actual thing and reducing it down or blowing it up, but keeping all the sizes and proportions similar to each other. This is how far they would be. If the Earth were this size and the moon were this size, this is literally how far away they would be. The moon is 250,000 miles away from us. Or to put it in another perspective, let's see if this will let me have my little drawing capabilities here. Okay, annotate, yes. So I want to draw something. If we were to take sort of Mercury and Venus and Mars and Jupiter and Saturn and Uranus and Neptune, we might even have room for Pluto down there. We could actually fit all the other planets of our solar system between the Earth and the moon. I'm not saying, because some people hear me say this, and I'm not saying this. I'm not saying they're this far away from us. I'm saying if you picked up the planet and put it between the Earth and the moon, we could actually fit all of our planets between us. So the moon is actually quite far away. Here we can see the planets again to scale. If this is the size of the sun, this is the size of the planets. Notice Earth almost disappears here, and Mars really does. And you can't even see poor Pluto with that little dot there. We've got other dwarf planets. Poor Pluto got demoted, but if it didn't, we'd have other planets along the way as well. Haumea, Makemake, Eris, and then we have Ceres here. Ceres is one of the asteroids. You can be more than one thing in the solar system. The Ceres is both an asteroid and a dwarf planet. But the sun is 99% of all the stuff in our solar system. You can see all of the planets put together don't come close to measuring up to the sun. Jupiter is also larger than everything else except for the sun in our solar system. The sun is a star. If you sort of look at it here, one of the things you might notice is the darkening that we have. That is called limb darkening, L-I-M-B. Your limbs stretch out. This is one of the ways in which we know that the sun is three-dimensional. It is actually three-dimensional. It's not flat. It's not Apollo's chariot wheel that's sort of going through here. And that's because the light on these edges here, on the limbs, are going off to the sides. But the light that's in the middle here is coming straight at you, so it's more intense. But we notice these sunspots here, they move because the sun rotates, but we don't have dark stripes that rotate. It stays dark on the edges. It stays dark on the limbs. So that tells us this is a three-dimensional object. Now, the star itself, our sun, is a fusion reaction. It's a nuclear reaction. What it's doing is it's taking hydrogen, the smallest element, and smashing it together to make helium, which is the second smallest element. And when it does that, they fuse together, and that becomes energetic. And we'll talk about that in chapters 15 and 16 mostly, so stay tuned. Around our star, we have planets. To be a planet, you have to be large enough to be spherical. So if you only have enough material to sort of become oddly shaped, potato-shaped, wedge-shaped, other things, you don't get to qualify as a planet. Also, you have to be the main thing in your orbit around. That's where Pluto got knocked off. But we got, we've had different debates on whether or not planets should be a certain way or other ways. So that is still something to be watched in the media and in definition. Science changes every now and then. Two main types of planets. We can have rocky planets like Mars, Earth, Venus, Mercury, all fit in this. We call them terrestrials. Terra means Earth-like. Or we have gas giants like Neptune, Uranus, Saturn, and Jupiter. So we've got the two different types, and we'll talk about why later in the semester. Around planets, we often have moons, or we can call them satellites. We tend to think of satellite as something that we put in orbit, but in fact, a satellite, we can usually say natural satellite, can also be something that is found in orbit from natural purposes. The moon is a satellite. This is Ganymede, which is the largest moon in our solar system around Jupiter. Then we have, as I mentioned, asteroids. Most asteroids, all but 2 of them, are small enough that they don't have enough gravity to pull them in to make them spherical. So they're odd-shaped, wedge-shaped, potato-shaped, oblong in different ways. Ceres, which I mentioned before, and Vesta here, we're just seeing the edge of Vesta here, are the only 2 that are large enough to be spherical or almost spherical. Most asteroids live between Jupiter and Mars, and we'll find out why later in the semester. Most comets, on the other hand, live way far out beyond Neptune. They're snowballs, they're icy, but when they come in closer to the sun, they begin to melt because it's hot, ice melts, and that's when they grow a tail. Some of them are periodic, like Hubble, or like Halley's Comet, comes around every 75 to 76 years. Some of them come around, but much, much more pronounced. Some come around every 1,000 years or every 1,000,000 years or so. And some are one-shot deals. They come too close to the sun and they melt and break apart. Sometimes they crash into the sun. Sometimes they crash into other planets like Jupiter. And we'll see that later in the semester too. So this is our solar system. And solar actually has a particular connotation. This Sol, S-O-L, is often the term we use for the sun in here as well. Now note one thing about this picture, it is not to scale. If this is the size of Jupiter, in fact, the sun would be about this big. So we can't really draw that and see what we want to see in all of this here. So these planets are not to scale. But what we can see is from this photo, or from this image, sorry, it's not a photo, we have the smaller planets clustered in the middle around the sun. The larger gas giants are further out. They're further out where it's cooler, where the gases aren't going to bubble away. Beyond this, we have nebulae. This is another close-up of the Orion Nebula. If you look here, this little measurement in the bottom there, that says 100,000 AUs. An AU is an astronomical unit. And an astronomical unit is 93 million miles. So that's something worth remembering. Astronomical unit. I need spell check here. 93 million miles. That is roughly the distance between the Earth and the sun. That's why we call it that along the way. That's a good term to remember and a good unit, a good number to memorize along the way. So it's not precise because sometimes the Earth is a little bit closer and a little bit further away. But we tend to think of it in terms of averages. So an astronomical unit is 93 million miles. 93 million miles on this picture would be this little dot right here, or this little dot right here. So when we're looking at this 100,000 AUs here, our solar system would fit within one of these dots. It's 1.5 million AUs all the way across. All of this gas and dust will actually collapse and coalesce under its own weight, under its gravity. Everything's pulling on everything else. And what will happen is it will eventually turn into stars. That's why this is a stellar nursery. Galaxies are big collections of stars. As I mentioned before, this is the Andromeda galaxy, our closest spiral galaxy. It's not the closest galaxy, it's the closest spiral galaxy. It has a couple of entourage galaxies, ours does too. We don't have any pictures of our galaxy from outside because it takes too long to get there and the picture to get back to us. It takes about 100,000 years for us to send a probe out, even if it was going at sort of a reasonable speed to get there, and then it would take 50,000 years for the picture to get back to us, to get an image like this from the outside. So that's not going to be happening. We do live in a spiral galaxy, but some spiral galaxies have this elongation in the middle. It's called a bar. So we actually live in a barred spiral. The spiral arms in our galaxy come off of an elongation like this. Some of them don't seem to have that. Notice here, Andromeda, going back, doesn't seem to have it. Here we have it in this one, and ours has one of these too. Some have very, very long elongations, some of them don't. But we're looking at the Milky Way from the inside when we look at it. If you go out to really dark patches in southern Indiana away from city lights, you can sometimes make it out. And as we spin on our planet's axis, we see the orientation of the Milky Way change around. So around the Milky Way, we also have big clusters of stars. Some of them are called globular clusters, and they can have 250,000 to 1,000,000, maybe a bit more stars. These are some of the oldest parts of our galaxy. So a lot of the people at IU study these. Here we have a setup of radio telescopes in the Atacama Desert, which is down in Chile. It's in the southern hemisphere. And if you know your astronomy, you would know immediately that this is from the southern hemisphere, sort of on the other side of the equator, when we're talking about South America, South Africa, Australia, places like that. And the reason why is these two fuzzy patches here. These are the large and the small Magellanic Clouds, and these are neighboring galaxies. These are the closest galaxies to us. Maybe there's one a little bit closer, but in general, we say that these are the two closest galaxies to us. They can only be seen from the southern hemisphere. You can't see them from Indiana. So when you see a picture like this, you know immediately where it came from. Again, here's another image of Andromeda. As we go through our orbit and as we spin on our axis, the way things look in the sky change. So that's why one picture looked like this, and now this picture looks like this. We can also see this was taken with a different kind of exposure. So you can get different details depending upon how you take the pictures. But this is our closest spiral, but it's not the closest galaxy. Note that there's probably a quiz question. Then we have clusters of galaxies. This is from 60 million light years away. So that means when we were taking this picture, the light that we're seeing in this picture actually started out from these stars and galaxies 60 million years ago. It took that long for it to get to us along the way. If we wanted to see what it looked like today, we'd have to wait another 60 million years. When we're talking about things like this, we're talking about the cosmic calendar, because it's so hard to think about things in terms of 60 million years and 500 million years and 14 billion years and stuff like that. So we have this idea of if the entire universe were in one calendar year, and we're sort of at the end of the year. The Big Bang started in January, and we sort of go through, and we can see the Milky Way didn't start until almost halfway through the year in May here. Our Earth didn't form until September, until the fall semester begins. And dinosaurs didn't appear until Christmas, and then they were gone before New Year's, so they didn't stay long. But human beings only appeared on the very last day. There's a video that I am putting up in your modules that has Carl Sagan's Cosmos series talking about the cosmic calendar. So please watch that, and it'll give you some more information on this concept. But as we are going through space, we're all in motion. You're in motion right now. And depending on where you are on the planet, you might be going at a different speed. If you are up on the North Pole, it takes you 24 hours to go around. If you're here in Indiana, it takes you 24 hours to go around. If you're down on the equator, it takes you 24 hours to go around. But notice if you're here at the North Pole, it takes you 24 hours just to go around that little bit. You're almost not moving at all. Whereas down at the equator, you have to go through thousands of miles. You're going over 1,000 miles an hour because it takes 24 hours to go around, but that's a long way to go around. Here in Indiana, we're going roughly 600 to 700 miles an hour. So as you sit here, you're going faster than a jet plane. While that's happening, we're also rotating and revolving around the sun. Our rotation is our sort of the way we go around our axis. So if you sort of think about spinning a basketball, that's rotating. Revolving is moving around something. So those two words are not exactly interchangeable usually, although sometimes I'll slip up and say one or the other. So as it's revolving around the sun, it takes 365 plus a little bit more days to go around the sun. That's a year. So our year is dictated by our movement around the sun. We're also angled. Notice this little angle here. So sometimes we're angled towards the sun in the north, and sometimes we're angled away, depending upon whether or not we are at one point of the orbit or the other. When we're angled away, it's winter. When we're angled towards, it's summer. But notice it's opposite. Notice that word, opposite. That'll happen again and again and again, opposite. It's opposite in the south from the north. So when it's winter here in Indiana, it's summer in Australia. When it's summer here in Indiana, like it would be over here, it's winter in Australia. Those are always going to be opposites. And we're angled at 23.5 degrees. So we're spinning at 23.5 degrees. That is called our ecliptic angle. So the angle of the ecliptic is 23.5 degrees. As we're moving around the sun itself is moving around the galaxy. So the whole galaxy is spinning. There really should be a little bit of a bar here in the middle here. But as we're going around, we're sort of going up and down around the center of the galaxy. And it takes about 250 million years for us to get there. We're actually about 30,000 light years away from the center, which means when we look at the middle of our galaxy, the light we get there, in fact, is about 30,000 years old. We're sort of on the edge, again, of the galaxy. If we were in the middle, there's a lot of light and radiation there, not so good for us. The middle is called the bulge. This elongation thing here is called the disk. We're looking at it edge on. The rest of all of this stuff is called the halo. And a lot of the mass is in the halo. Notice these little things here. These are these globular clusters. And I showed you a picture of one of these. This is the globular cluster close up. There are several hundred of them around our galaxy. So as we are in that galactic movement, the whole universe is also expanding. And it looks like most things are expanding away from us. Imagine you're in this little raisin cake here, and you are standing on this one raisin. We'll call it the local raisin. As you're in the oven watching everything, you're watching everything expand away from you. You're just sitting here on the raisin, and everything everywhere else seems to be going away from you. But here's the interesting thing. If you were over here on raisin number 3 rather than the local raisin, it would look exactly the same to you. Everything's still going away from you. You're just sitting there. So there's no real center to the universe. We're not the center of the universe. You may know someone who thinks they're the center of the universe. There's no real center of the universe here. So are you ever sitting still? The answer is no. Here in Indiana, as we rotate on the axis, you're going 1,000 kilometers, let's say 600 to 700 miles per hour. While the Earth orbits, it revolves around the sun. Again, we're talking about 70,000 miles an hour or so. While the sun moves in the stars, while the Milky Way rotates, huge numbers here, notice. While the Milky Way itself is moving in the local group. Remember, as I said, the Andromeda galaxy here and the Milky Way are coming towards each other as the universe itself expands in different ways. So yes, we're moving quite a bit. So here's your task. If you ever get stopped by a policeman for speeding and he says, do you know how fast you are going? I dare you, I double dog dare you to pull out this and say, yes, officer, I know I'm going 700 miles an hour as the Earth is rotating, and I'm going and do all of that sort of stuff. And when they take you to court, I'll bring my camera and we'll make the video go viral. I will not bail you out, but there you go. So I hope you've enjoyed this. I look forward to our next lectures, and just keep going through the modules, and I will see you on Zoom.